Let me ask you something. If engineers can calculate everything, loads, stresses, safety factors, then why do so many structures not follow the so-called best solution? Why does it feel like the design is playing it safe, or worse, wasting material? People look at buildings and say, come on, this could have been lighter, this could have been cheaper, this doesn't look optimal at all. And honestly, on paper, they're often right. But here's the uncomfortable part nobody tells you. The best structure is usually the one we don't build. Because the moment a design becomes truly optimal, it also becomes fragile. In this video, I want to explain why real-world structures often walk away from the most efficient option on purpose. Not because engineers are lazy, not because they can't calculate, but because the real world doesn't behave like equations. People love the word optimal. It sounds scientific, it sounds objective, it sounds like there is one correct answer and everything else is a mistake. In structural engineering, people ask this question all the time. Why didn't they choose the optimal solution? At first glance, it feels like a fair question. If you can calculate loads, stresses, and safety factors, then surely there must be a best option. The strongest structure, the lightest structure, the cheapest structure, the safest structure. So why not just pick the optimal one? The problem is simple but uncomfortable. Optimal only makes sense if you already agree on what you are optimizing for. And in real projects, that agreement almost never exists. On paper, optimization looks clean. You define a goal, you set constraints, you run calculations, you get an answer. In reality, every project starts with multiple goals pulling in opposite directions. Make it stronger, but also cheaper. Make it lighter, but also easier to build. Make it innovative, but also familiar enough to pass approval. Make it efficient, but also robust against mistakes. Each one of these sounds reasonable. Together, they fight each other. If you optimize for strength, you usually add material. If you optimize for cost, you remove it. If you optimize for speed, you simplify the design. If you optimize for performance, you add complexity. So when someone says, this is the optimal design, the first question should be, optimal according to which metric? Because the answer changes everything. Engineers often talk about optimal solutions in school, but school problems are polite. They come with fixed assumptions. Loads are clear. Materials are available. Construction quality is perfect. Nobody changes their mind halfway through the project. Real life is not polite. In real life, optimization is fragile. You can design a structure that is mathematically elegant, extremely efficient, and perfectly balanced. And then one small assumption changes. The steel grade is substituted. The concrete quality varies. The contractor uses a different construction sequence. The schedule gets compressed. The budget gets cut. Suddenly, the optimal solution is no longer optimal at all. This is why experienced engineers tend to be suspicious of designs that look too perfect. They know that optimization usually lives at the edge, and edges are dangerous. Another uncomfortable truth is this. An optimal solution on paper is often optimized for a world that doesn't exist. It assumes ideal conditions, ideal workmanship, ideal supervision, ideal execution. But structures don't live in equations. They live on construction sites. They live in weather, in delays, in misunderstandings, in small mistakes that nobody notices until it's too late. So when people say, this design is not optimal, what they often mean is, this design is not optimal in a simplified model that ignores reality. There's also a psychological trap here. People assume that engineers are always chasing the best possible solution, that if something looks conservative or inefficient, it must be due to laziness or lack of skill. But engineering is not a beauty contest for equations. It's a risk management profession. The real question engineers ask is not, what is the best structure? It is, what is the worst thing that can realistically happen, and will this structure survive it? That shift in mindset changes everything. From the outside, two designs may look very different. One looks elegant, slim, and efficient. The other looks heavier, simpler, maybe even boring. To a non-engineer, the first one feels smarter. The second one feels wasteful. But often, the second one is deliberately chosen because it tolerates uncertainty better. Optimization hates uncertainty. Robustness embraces it. And here's the part that many people don't like to hear. The more optimized a system is, the less forgiving it becomes. When everything is tuned to perfection, there is no room for error, no margin for misunderstandings, no buffer for real-world messiness. That's why engineers often draw a clear line between academic optimization and practical design. Academic optimization asks, how far can we push this? Practical design asks, how badly can this go wrong? These are very different questions. This is also why you often hear experienced engineers say things like, this works in theory, but I wouldn't build it. They're not rejecting the math, they're rejecting the assumptions behind the math. Because structures don't fail when equations are wrong. They fail when assumptions quietly stop being true. So when someone asks, why wasn't the optimal solution used? A more honest answer might be, because the real world is not optimized. It's constrained, it's inconsistent, it's political, it's economic, it's human. And humans are not variables you can fully control. In engineering, optimal is not a destination. It's a moving target that shifts every time a condition changes. That's why in practice, engineers rarely design for the absolute best-case scenario. They design for acceptable outcomes across a wide range of imperfect conditions. And that brings us to an important realization. In real projects, there is no single optimal solution. There are only trade-offs that someone has to accept. The moment you understand that, the original question changes. It's no longer, why didn't they choose the optimal solution? It becomes, which compromises were they willing to live with, and why? And that question leads us much closer to how real structures are actually designed.
There's a moment in almost every project where design looks perfect. The numbers work, the drawings look clean, the material usage is efficient. On paper, it's beautiful. And then someone asks a very simple question. Okay, but how are we actually going to build this? That's usually when things get awkward, because the dirty secret of structural design is this. A lot of optimal designs are optimized for calculation, not construction. They assume perfect execution, perfect sequencing, perfect coordination between trades, perfect tolerance control. And construction sites are none of those things. In theory, a structure might rely on load paths that are very precise. Members need to engage in a specific order. Connections need to be tightened in a specific sequence. Temporary supports must stay until a certain stage. Miss one step and the whole logic collapses. Now imagine explaining that to a contractor who is under time pressure, budget pressure, and weather pressure. That's usually when things get awkward, because the dirty secret of structural design is this. A lot of optimal designs are optimized for calculation, not construction. They assume perfect execution, perfect sequencing, perfect coordination between trades, perfect tolerance control. And construction sites are none of those things. In theory, a structure might rely on load paths that are very precise. Members need to engage in a specific order. Connections need to be tightened in a specific sequence. Temporary supports must stay until a certain stage. Miss one step and the whole logic collapses. Now imagine explaining that to a contractor who is under time pressure, budget pressure, and weather pressure. That's usually when things get awkward, because the dirty secret of structural design is this. A lot of optimal designs are optimized for calculation, not construction. They assume perfect execution, perfect sequencing, perfect coordination between trades, perfect tolerance control. And construction sites are none of those things. From an engineer's perspective, a design might be optimal because it minimizes material, From a builder's perspective, the same design might be a nightmare. Too many unique components, too many custom connections, too little tolerance for on-site adjustment. And here's the uncomfortable truth. Construction errors are not rare, they are normal. Not because people are careless, but because construction is done by humans in imperfect conditions under changing constraints. So engineers have to ask a question that never shows up in optimization equations. What happens if this isn't built exactly as intended? If the answer is nothing critical, the design is robust. If the answer is things could go very wrong, the design is risky. And optimal designs tend to be risky. Think about tolerances. On paper, two steel members meet at a perfect angle. In reality, one is a few millimeters off. The hole doesn't line up. The connection needs to be forced. A conservative design absorbs that error. An optimized one doesn't. Now multiply that across hundreds or thousands of connections. This is why many experienced engineers instinctively simplify designs, even if it means using more material. Because simplicity is not stupidity, it's a form of risk control. Another issue is sequencing. Some structures are only stable after everything is in place. Until then, they rely on temporary supports, temporary bracing, temporary assumptions. On paper, that's fine. In reality, temporary works are where many failures happen. They're often rushed, poorly documented, and sometimes ignored entirely. So when an engineer chooses a heavier beam, a thicker slab, or an extra brace, they're often buying insurance against construction stage failure. That insurance doesn't show up in a spreadsheet, but it matters. There's also the issue of skills. Not every construction team has the same experience level. Not every site has access to specialized labor. Not every region has contractors comfortable with complex geometries. A design that is optimal in a high-tech lab environment might be completely inappropriate for a real-world site with limited resources. So, engineers adjust. They choose systems that builders already understand, details that are familiar, methods that have been used before. From the outside, this looks conservative. From the inside, it looks responsible. And then there's time. Optimization often assumes unlimited time for careful execution, but projects rarely have that luxury. Schedules get compressed, delays stack up, pressure builds. When time gets tight, complexity becomes dangerous. A simple structure can be built fast and safely. A highly optimized one usually cannot. This is why you'll often hear engineers say things like, "I could design this lighter, but I don't trust the site conditions." That's not arrogance, that's experience talking. They've seen what happens when designs assume too much discipline on site. And finally, there's coordination. Structural design doesn't exist alone. It has to coexist with architecture, mechanical systems, electrical systems, fire protection, and more. So, an optimized structural layout might clash with ducts, with pipes, with equipment. So, the structure gets adjusted, bent, compromised. At some point, the original optimal idea becomes unrecognizable. Rather than fighting every conflict, engineers often step back and say, let's choose something simpler that everyone can work around. Again, not optimal on paper, but workable in reality. So when people ask, why didn't they use the best structural solution? A very honest answer is because someone actually had to build it. And building things is messy. Engineering that ignores that mess might look smart right up until something goes wrong. And that's why the gap between optimal design and real structures is not a failure of engineering. It's engineering adapting to reality.
There's a sentence engineers don't like to say out loud, but everyone knows it's true. Design decisions are not driven by physics alone. They are driven by who takes the blame when things go wrong. This is where the idea of optimal structure quietly breaks down. Because once a project leaves the classroom and enters the real world, optimization gets a new variable, and it's a heavy one: liability.
On paper, two designs may both satisfy the code. They may both be safe. They may both work. But they do not carry the same risk, not structurally, but legally. And that difference matters more than people think. Let's say you design a very efficient structure. Material usage is low. Margins are tight but compliant. Everything checks out. Now imagine 10 years later, something fails. Maybe it's not even a collapse. Maybe it's excessive cracking, unexpected deflection, a serviceability issue that triggers complaints. The first question won't be, was this mathematically optimal? The question will be, was this a reasonable design? That word, reasonable, is terrifyingly vague, and it's not defined by equations, it's defined by precedent. In engineering, being right is not always enough. You also have to be defensible. That means if you end up in a meeting, a court, or a courtroom, you need to explain why you made the choices you made. And here's the uncomfortable reality. It's much easier to defend a conservative decision than an aggressive one. You can say, we added extra capacity for robustness. We allowed additional margin for construction uncertainty. We followed common industry practice. Those sentences protect you. Try defending this instead. Yes, it was very efficient, but there was almost no redundancy. That's a much harder sell. So engineers learn, sometimes painfully, that optimization has a social cost, not to the building, to the people who sign the drawings. Every structure has a name attached to it. Someone stamps it. Someone takes responsibility. And responsibility changes how you think. You stop asking, what is the lightest possible solution? You start asking, what solution can I still stand behind years from now? That shift alone kills many optimal designs. There's also the issue of asymmetry. If a structure is over-designed, the consequences are usually financial. More material, higher cost. If a structure is under-designed, the consequences can be catastrophic. The risk is not symmetric. So optimization that saves, say, 5% of material might increase perceived risk by 50%. That trade-off almost never wins. Now let's talk about cost, but not the way people expect. People assume conservative designs are more expensive. Sometimes they are. But complexity is also expensive. An optimized design often requires more detailed analysis, more coordination, more precise construction, more supervision. Those costs don't always show up in the structural budget. They show up everywhere else. So a cheaper structure on paper can make the entire project more expensive in reality. Clients don't always see that up front, but engineers do. And then there's insurance. Professional liability insurance does not care how elegant your equations are. It cares about risk profiles, unusual systems, uncommon details, pushing limits. Those things raise eyebrows. Sometimes they raise premiums. Sometimes they trigger exclusions. So when an engineer says, "This solution makes me uncomfortable," they might not be talking about physics at all. They might be talking about exposure. Another factor is collective responsibility. Most projects are not designed by one person. They are reviewed, checked, approved. The more unconventional a design is, the harder it is to get everyone comfortable with it. Reviewers tend to ask more questions. Approvals take longer. Comments pile up. At some point, the team asks a simple question: is this fight worth it? Often the answer is no. So the design gets simplified. Margins grow, efficiency drops. Not because the team can't do better, but because the system punishes those who try. And here's something rarely discussed outside the profession. Engineering culture remembers failures far longer than successes. Nobody remembers the building that used 10% less steel, but everyone remembers the one that had problems. That collective memory shapes behavior. It creates invisible boundaries. This is safe territory. That is risky territory.
Optimal designs often live just outside those boundaries. Now add one more layer: contracts. Design responsibilities are often fragmented. Structural engineers design structure. Contractors choose means and methods. Temporary works are sometimes not our scope. That fragmentation creates gaps. An optimized design might rely on assumptions about construction that nobody contractually owns. Who's responsible if those assumptions fail? If the answer is unclear, the design becomes dangerous, not structurally, but legally. So engineers pull back. They choose solutions that are robust even if others don't perform perfectly. That robustness costs material, it costs efficiency, but it buys clarity, and clarity is valuable. This is why you often see structures that look heavier than necessary, why redundancy is built in, why margins seem generous. From the outside, it looks like inefficiency. From the inside, it looks like survival. Because engineering is not just about making structures stand up. It's about making decisions you can live with. Years later, under scrutiny, with incomplete information, in hindsight. So when people ask, why didn't they choose the optimal solution? A deeper answer is, because the optimal solution wasn't the safest one for the people responsible for it. Not morally, professionally. And that reality shapes structures far more than most people realize.
At some point, every engineer hears the same complaint. Why are building codes so conservative? From the outside, it's a fair question. Codes add rules. Rules add limits. Limits seem to block innovation. So it's tempting to think codes are just outdated, slow, or overly cautious. But that misses the point. Building codes are not written to find the best structure. They are written to prevent the worst outcomes. And those are very different goals. Optimization asks, how far can we go? Codes ask, how badly can this go wrong and how do we stop that? Codes are born from failure. Almost every major rule in a modern code exists because something collapsed, cracked, burned, or killed people. Not because an engineer once found a better equation. So when you read a code requirement, you're not just reading theory, you're reading a memory of something that went wrong badly enough that society decided this should never happen again. And memories don't care about elegance, they care about survival. This is why codes are blunt instruments. They don't assume perfect execution, they don't assume perfect materials, they don't assume perfect understanding. They assume mistakes. They assume variability. They assume people will misunderstand drawings. They assume construction quality will vary. They assume maintenance will be imperfect. In other words, codes assume reality, and reality hates optimization. An optimal design often sits close to limits, stress limits, deflection limits, stability limits. Codes push you away from those edges. They add safety factors, partial factors, load combinations that almost never occur together. From a pure optimization standpoint, that looks wasteful. From a societal standpoint, it's intentional, because when things go wrong, they rarely go wrong one at a time. Loads stack, errors compound, assumptions break simultaneously. Codes are designed for that chaos. Another thing people don't realize is that codes are written for the entire industry, not just the best engineers. A code has to work for experienced professionals, young graduates, overworked teams, underfunded projects. It has to protect against both ignorance and overconfidence. If codes were written assuming perfect judgment, they would be dangerous. So they are written assuming average behavior, sometimes below average. That alone kills many optimized solutions, because optimization usually assumes high competence at every step. Codes also don't reward cleverness. If you find a very efficient but unconventional solution, the code will often ask you to prove repeatedly that it's safe. More calculations, more checks, more peer review.
That friction is not accidental. It slows down risky ideas, not because they're wrong, but because they're unfamiliar, and unfamiliar things fail in unfamiliar ways. Codes are conservative not because engineers lack imagination, but because society doesn't want to experiment on occupied buildings. Another uncomfortable truth: codes are political documents. They are written by committees. Committees balance interests: safety, cost, constructability, public perception. Every rule is a compromise. So when a code sets a minimum thickness or a maximum slenderness, it's not claiming that number is optimal. It's saying, below this, too many bad things have happened. That threshold might be higher than necessary for some projects, lower than ideal for others, but it's uniform. Uniformity is not efficient, but it's enforceable. And enforcement matters, because a rule that can't be enforced might as well not exist. Optimization often creates gray areas. Codes try to eliminate them. That's also why codes lag behind research. By the time something becomes a code rule, it's usually been tested, debated, and proven in practice. Years, sometimes decades. This frustrates people who want to push boundaries. But codes are not there to help pioneers. They're there to protect the public from widespread risk. Another key point: codes don't know your project. They don't know your site conditions, your contractor, your budget, your risk tolerance. So they assume the worst reasonable case. That means your design might be safer than required, but the code doesn't care. It cares that the weakest design still doesn't kill anyone. And finally, there's this: codes shift responsibility away from individuals. If you follow the code, you're not claiming your design is perfect. You're saying it meets an agreed societal minimum. That shared baseline protects engineers, clients, and regulators. Optimization, by contrast, personalizes responsibility. If you push beyond common practice, you own that risk. Some engineers are willing to do that, many are not, and the system is designed to favor the cautious ones. So when people say, "Why doesn't the structure follow the optimal solution?" sometimes the simplest answer is because the code exists, not as an enemy of engineering, but as a memory of its failures. Codes don't aim for the best structure. They aim to stop the worst ones from ever being built. And in doing so, they quietly pull every design away from the edge, away from optimal, and toward something society can live with.
Here's something every experienced engineer learns the hard way. No project stays the way it was originally designed. Never. Functions change, layouts shift, budgets move, schedules compress, and when that happens, the structure has to adapt. This is where optimal designs start to fall apart, because optimization assumes stability, not structural stability, but decision stability. It assumes that loads are fixed, that usage is known, that nothing significant will change after the calculations are done. Real projects laugh at that assumption. A client might say, "We might add another floor later," or "That equipment is heavier than we thought," or "Can we open up this space?" Each of those sounds small. To an optimized structure, they are not. Optimized designs are usually tuned very tightly to a specific scenario. Change the scenario and the whole balance shifts. A beam that was perfectly sized suddenly has no reserve. A column that worked fine is now overstressed. A slab designed for minimal thickness starts cracking. In contrast, a more conservative structure absorbs change quietly. It doesn't complain, it doesn't demand redesign, it just takes it. That flexibility is not an accident, it's often intentional. Engineers know that buildings are not static objects. They're used, modified, abused, and misunderstood over decades. So they ask a question that optimization models usually ignore. What will happen when someone wants something different? And someone always does. Another thing people underestimate is how early optimization happens. Structural optimization often locks in decisions very early in the project, when information is still fuzzy. Loads are estimated, architectural layouts are preliminary, Mechanical systems are not finalized. Optimizing too early is dangerous. You are squeezing margin out of a design based on guesses. If those guesses turn out to be wrong, you pay for it later with redesign, reinforcement, or compromise. That's why many engineers prefer to waste a bit of material early on. It buys them freedom later. Freedom to adapt, freedom to respond, freedom to say yes instead of no. From the client's perspective, this matters. A structure that can accept changes without major cost is valuable, even if it wasn't the lightest option on day one. But there's also a human side to this. Projects involve many people: architects, engineers, clients, contractors. Not everyone understands structural limits. People will ask for changes without realizing the consequences. If the structure is already at its limit, every small request becomes a problem. That creates friction. Meetings get tense. Blame starts flying. An optimized structure can turn normal project evolution into a constant series of conflicts. A robust structure, on the other hand, creates peace. It quietly absorbs poor decisions. That might sound cynical, but it's real. Engineers often design not just for loads, but for human behavior. And human behavior is unpredictable. There's also the long-term view. Buildings outlive their designers. What starts as an office becomes a lab. A warehouse becomes a gym. A residential building gets new equipment, new partitions, new uses. Codes change, expectations change. Structures that were optimized for a narrow original use struggle in these transitions. Structures with extra capacity don't. So when an engineer chooses a thicker slab or stronger frame, they might be thinking 30 years ahead, not just a handover. That kind of thinking is invisible in calculations, but very real in practice. Another issue is that changes rarely come one at a time. A project might handle one change fine, two changes with some effort, but optimized systems tend to fail suddenly, not gradually. They don't bend, they snap. That brittleness is dangerous in long, messy projects. So engineers deliberately move away from the edge. They create designs that are forgiving, not perfect. And here's the key insight. Optimization is efficient if the future is predictable. Construction and buildings are not. So optimal designs work best in environments with fixed requirements, controlled execution, limited future change. That's why you see them more often in machines than in buildings. Buildings are social objects. They serve people who will misuse them, repurpose them, and demand more from them over time. So engineers compromise. They give up peak efficiency in exchange for adaptability. And from a distance, that compromise looks like inefficiency. But from inside the project, it feels like wisdom. So when people ask, why didn't they design it in the most optimal way? Another honest answer is, because we knew it wouldn't stay that way. And that realization that change is guaranteed is one of the strongest forces pushing structures away from theoretical optimality.
So after all this, let's step back. We started with the simple question, why don't structures follow the optimal solution? After 5 layers, the answer should be clear now. It's not because engineers don't know how to optimize. It's not because they're lazy. It's not because they're afraid of math. It's because real engineering is not a search for the best answer. It's a search for an answer that survives reality. Reality includes construction errors. It includes legal responsibility. It includes building codes written in blood. It includes clients changing their minds. It includes buildings being used in ways nobody predicted. An optimal solution assumes a stable world. Engineering assumes an unstable one. That difference changes everything. If you optimize too hard, you remove margin. If you remove margin, you remove forgiveness. And unforgiving systems don't last long in the real world. This is why experienced engineers don't ask, is this the most efficient structure? They ask, is this structure tolerant of mistakes? Mistakes in construction, mistakes in assumptions, mistakes in future use, because mistakes are guaranteed. The goal of engineering is not elegance, it's endurance. A structure that looks slightly over-designed often survives decades of abuse, modification, and neglect.
A structure that is perfectly optimized often struggles the moment something changes. From the outside, that looks like inefficiency. From the inside, it looks like wisdom. And this is where a lot of misunderstandings come from. People compare structures the way they compare products. Lighter is better, cheaper is smarter, more efficient must be superior. But buildings are not gadgets. They don't get replaced every few years. They don't live in controlled environments. They don't come with user manuals that people actually read. They live in the real world, where conditions drift, people improvise, and decisions pile up over time. So engineers design accordingly. They give up the last bit of efficiency to gain robustness. They accept heavier sections to gain flexibility. They follow codes, not because codes are perfect, but because codes represent collective memory of what happens when things go wrong. This also explains why engineering progress often looks slow. It's not because nothing changes. It's because every change has to survive reality, not just calculation. Optimization pushes boundaries. Engineering protects society. Those two forces will always be in tension, and that tension is healthy. Because a world optimized only for efficiency would be incredibly fragile. So the next time you look at a building and think, this could have been done better, you might be right, mathematically. But engineering is not about being mathematically right. It's about being right when things don't go as planned. And that's why structures rarely follow the optimal solution. Not because engineers can't do better, but because they know exactly what happens when better leaves no room for error.